the both stress are positive. So we have tensile stress, and also sigma r is less than sigma t or sigma theta when we have rotating. So what would be the stress value? I mean, we can prove so the tangential stress can be calculated by this equation, and radial stress can be obtained by equation 355 down here. So what would be the term? Rho would be the mass density of cylinder. So the blower, the disc or flywheel, it's made of a material. What would be the mass density of that? Omega is angular speed. The unit is radian per second. So no other unit should be used here. Mu is the Poisson ratio for the material. Whatever is the material, it's a property of that material. Ri is the inner radius, Ro is the outer radius. We have the terms right here. R is the radial distance of the point that you are looking for, its stress. So if this is the cross section of the cylinder, if you are looking for the stress at this point, whatever is the radial distance should go there. And I just have another mu, which is the Poisson ratio, 3 plus mu times r squared. So it's going to give me the tangential stress. Radial stress is going to be the same up to here. This positive has been changed to a negative, and here I don't have any mu, and I have just negative r squared. So this is how we can So if I want to plot sigma or a normal stress versus R, R goes from inner radius up to outer radius. How it's going to change? For the radial stress, if I plot this, I'm going to get something like this. At inner radius and outer radius, sigma R is going to be 0. At this point, it's going to be at the maximum value. Sigma max, sigma R max. So this R max is a square root of Ri, Ro. I could ask you find this value by differentiating this with respect to r and set it equals to 0. The extreme value is gonna be, it's gonna occur at this r. So this is how we can find that r. For tangential, it's gonna look like this. Something like this. So this is sigma theta or tangential or hoop stress. So as you see, it's greater than sigma r, and you can see the maximum tangential occurs at sigma at r equals to ri. And if you want to find the value, just plug in r equals to ri on this equation. If I ask you what would be at which radius we are going to have tau max, the shear stress, maximum shear stress, you should see at which r we are going to have the maximum difference between sigma 1 and sigma 3. So at inner radius, I'm going to see the maximum difference occurs at r equals to r, because the difference between sigma theta and sigma r is going to be at its maximum value. Here I have the tangential maximum stress at r equals to ri. The value is going to be this. I just plugged in r equals to ri, and I got that equation. And the maximum radial stress by plugging r equals to s square root of ri ro can be obtained by this equation. Good? Yes?
So you have sigma r max detailed out. Would that be at the neutral radius? Or what does the, I mean, like the x value that max down to?
Here?
It's original with the r max equals the sort of r io.
Oh, you wrote it. Okay. Never mind. My bad.
Any other question? So this is how the radial stress and the tangential stress is developing over the rotating cylinder. So before I work on one example, the next topic, which is going to be the last topic on cylinders, would be press fit. If you have two cylindrical components, one is at the smaller radius and the other one is at the larger radius. So suppose we have a shaft and hub. This is the hub and this is the shaft. One way, and this is, suppose this is a smaller cylinder, and this is the larger cylinder. The example can be two tubes or a shaft and hub. one way that you can attach these two is if this is the inner radius of inner diameter of a larger component, and this is the outer radius, outer diameter of a smaller component. If a smaller component has the outer diameter slightly greater than inner diameter of the larger component, you can press this and fit into the larger component. So we call it press fit. So this is how you can assemble these two components together and get one cylindrical component. So DO for smaller is slightly greater than the DE for the larger component. You press this and fit into the larger component. And due to this press fitting, you are going to develop some pressure. Due to this press and fit into that, you are going to develop some pressure. This one is going to be under internal pressure, and this one is going to be under external pressure. We call it PF, which is which we call interference contact pressure. So this pressure is coming due to the press fitting. So it's gonna generate the external pressure for a smaller component due to the press fitting, and it's gonna generate internal pressure for the larger component. So this is the case. And if I ask you, you have seen this before. For this one, just look at, or this one, it doesn't matter, inner pressure or external pressure. So for external pressurized cylinder, the cylinder is under external pressure of PO. What would be the radial maximum pressure? It's going to be negative PO, and it occurs at the outer radius. So at the outer radius of a smaller component, the radial stress is negative PF, which is this one. And for this one, when it's under internal pressure, the maximum radial stress is gonna occur at inner radius, which is this is radial. When it's under internal pressure, the maximum radial that occurs here, which is equals to negative PO. We have covered this before. So now I'm gonna work on one example. two concentric AISI 1040 tube are connected by press fit. At PF equals to 110 megapascal. So we have two tubes. I will draw the dimensions shortly. The larger tube has the diameter of 100 millimeter and inner diameter of 80 millimeter. Larger tube. The smaller tube has an outer diameter of slightly greater than 80 millimeters. Suppose it's 81 millimeter. An inner diameter of 60. So a smaller tube press fitted into the larger tube. So it's 81 millimeter to press fit into this larger tube, and this is going to generate this press fit pressure, which is 110 megapascal. After you do that, you are going to have one single component. Hundred $60 and the contact diameter is 80 millimeters. So now these two tubes are attached together, and just imagine one shaft is passing through this and it's going to rotate. So this pressure at the contact surface is making external pressure for a smaller component and internal pressure for the larger tube, which makes the sigma R equals to negative PF. So it's a compressive stress. But since it's rotating, it's going to generate positive. As you see, the radial stress is going to be positive. The question is, at which speed the radial stress increases to 0. It's going to start rotating. At which speed the magnitude of the radial stress here is going to be 0. Means if we look at rotating cylinder, at which omega the radial stress is going to be equal to 110 megapascal. This can be cancelled out with that negative 110 megapascal. And at that speed, we are going to lose the connection between two tubes. So I can say what would be the maximum possible or allowable speed for these joints.
Are we saying that we press fit this together and then we're spinning the whole combined mass of two at the same time?
Yes.
Okay.
Yeah. Yes.
So if we push it together, it's being held together just by like friction and that force. But
Yes.
if we spin it fast enough, the outside will like stretch enough that it will be too big and it'll fall apart. That's what we're
That's
finding is how fast when
That's
it'll fall apart.
That's or in other hand, at which speed the summation of the stress is gonna be 0. Due to that one, they are gonna stretch because we have a strain, radial strain, and at which speed we are gonna have a 0 strain or a stress. I mean the difference between the strain. It's gonna be 0. So this is what we are gonna find.
So we're talking some real RPMs.
Yes.
Yeah.
This is a real precedent.
It's a whole millimeter. It's huge.
I'm saying, like,
Also that is a good point.
like I could see like measuring like the force where like some
Or
like,
where
like,
it starts to
like,
slip,
yeah.
force to slip, like how much torque you can handle before it slips. I can see that stuff. But as far as just
So PF is 110 megapascal. So let me sigma R is negative 110 megapascal. So I'm gonna use this equation
Friction.
that we have here, and at this radius, at radius of 40, I would like to get sigma R equals to positive 110 megapascal. At R equals to 40 millimeter, which is the contact radius, set sigma R equals to positive 110 megapascal. So it's gonna be rho for that material 1040 AISI is 7850 kilogram, and Poisson ratio is 0.3. It's the material was given. Pardon? So it's gonna be 110 10 power 6 equals to just write 3 plus mu is 0.3 divided by 8, rho is 7850, omega square times Ri square. Inner radius is 30 millimeter, which is 0.03 square, plus outer radius is 100, which is 0.05 square, minus Ri 0.03, 0.05 divided by R square, at which R I'm looking for the stress at R equals to 40 millimeter, 0.04 square minus, yes,
R-I and R-O squared on top as well.
thank you. Thanks. So right hand side in Pascal, left hand side every unit is in psi. So we can solve for omega. Omega square, I just write the final answer. Omega is 9288 radian per second. Or if you change it to RPM, it's gonna be 88,700 RPM.
That's less than I thought.
So yeah, you should calculate.
That's just where it equals 0.
Oh yeah, that's where it equals 0. It doesn't mean it's tall or something that big.
You no longer have friction.
Technically, there's
Yep.
still
There is no friction
So
for.
it's just chance.
Let's test this. Where can we get a motor that spins?
Alright, if you
Tesla.
can take
That's all I'm
1040
saying,
steel and press it in under those dimensions, I will give you $100.
Also,
That's
Yes.
the denominator is at
Hello,
0.04 quantity squared.
Yes. Yeah. And
Just to get it
this is square, R square. What is the R?
You need a chance.
You can have a hand check.
So specific.
So you have this connection until you reach to this speed. If you reach that speed, since you are gonna have zero radial stress, you don't have any friction, and you are gonna lose the joint.
I don't know what's talking about any of this. Just messing around with this computer, it's doing tech.
It's not slow. It's not a bite.
This-
Any question on this? All right. Let's look at one of the M files that you can find on the MVP. So we look at thin cylinder, which was N capital C underline 2. We look at capital K, capital cylinder underline 2. And this is talking about the rotatory, capital R, capital C, cylinder, underline 2. So if you run this, you get this window, rotating cylinder analysis. We have a rotating cylinder, we would like to do analysis. What would be the inner diameter? Inner diameter is 60 millimeter. The units are not in English or they are not in US, so we are gonna, I don't check mark that, so I will just enter 60 E negative 3.
So it's in meters.
Yes, it should be.
Oh, that's all.
The outer diameter is 100
Or you could do that.
E negative 3. Material. Here I have medium carbon steel AISI 1040. So for some material you can check. If you couldn't find, just set user specified and enter the values. So angular speed that I got is 9288. We just want to check something. And at which radius you are looking for the stress. So I'm looking for stress at this radius, which is 40. You can pick another radius. What I want to get, this.
How much extra credit would it be to remake some of this software?
I
Because
don't know why.
that's
pay for your mental health care.
I'm good at that stuff. I did that at board.
Yeah, it's not.
All right. No, the problem with my laptop is too slow.
It doesn't on
It's difficult. can, but we should go to the file. I don't want to go. No, my laptop is too slow, so it takes time to bring the result. I know, even in my so, all right. Here, the stress at the radial location of interest. The location of interest was 4D. At that 4D, I should get the radial stress almost equals to 110 megapascal, which is 110 and 3.
It's not deep because it's
1, 2, 3, 4, 5. I don't see the number. So it's going to be 110 megapascal almost, which is equals to the press fit that we had in this problem. So this is how we can find the radial stress and tangential. Good? All right. The last topic on
So is that another the extra credit
for what?
to fix the MATLAB codes?
I appreciate, yeah. If
He will
you,
appreciate you. That's what you get.
What is that worth in GPA?
I,
He won't fail you just for asking.
neutral.
Lateral movement.
all right. The last topic is what would be the stress developed on the press fitting components. I explained that. Now I'm going to look at the equation. As I said, when you do the press fitting, the smaller component is slightly larger than the larger cylinder. So we define as a delta radial interference. Delta is the outer radius of the smaller component minus the inner radius of the larger tube or cylinder. Just the difference between these two is gonna give me the delta. So due to this difference, I'm gonna get some pressure. Pressure due to the press fitting. So this pressure is gonna be the external pressure for a smaller component and internal pressure for the larger component. If I know the P, I can find the stress developed here in the larger component and the stress developed on a smaller component. So I'm gonna find the PF due to the delta. So this equation right here, 356, is gonna give you this PF. Let's look at the terms. It's asking about the radial interference, how much would be the delta, or what would be the radius at the contact. Here in this example was 4B, the radius. So R is the radius at the contact surface. EO is the modular plasticity for larger or outer components. RO is for outer radius, which is 50. R again is the radius at the contact surface. Mu is the Poisson ratio for the larger component, and this side is for the smaller component. EI, R, RI. RI is this, which is 30. Yes.
Do we always assume that the smaller component takes the inner diameter, takes the inner diameter of the larger?
Yes. And if both cylinders are of the same material, you have the same EI, EO, you have the same V, Poisson ratio. You are going to end up to something like this. And these are coming from just plugging the numbers on these two equations. I have a cylinder, it's under internal pressure. What would be the tangential stress at this radius? You can find that for the outer member. So for the inner member, what would be the tangential at this radius? You can just plug in the numbers on